Hi, everybody. Thank you so much for the opportunity to present in this conference. My name is Alberto Madrid, and I'm an associate professor at Liga University. Today, I will be talking about perspective on market design for a low carbon economy. And I would like to start with the motivation related to the way that we see that different electricity systems are evolving. So given that this is a conference in South Korea, I start with the overall portfolio of generation that you have during the last decade. And as you can see, it has been relatively stable. There has been some increase in the overall participation, and this probably all of you have seen that the uh, increased participation of natural gas is something that is affecting many countries. One thing that we're going to be seeing towards the future is more and more participation of different renewable energy sources. And that is actually this brown part that we have in the upper component of the graph. And I'm going to be talking mostly about the US market because it's the one that I know better. So, for example, these are projections by the Energy Information Administration, which is the statistical agency in the US, in which we see that renewables are going to be becoming a significant part of the generation portfolio, right? So, like, we still expect that natural gas is going to be an important component, similar to what is happening in Korea. But we expect that renewables are going to be a much larger participant in terms of the overall electricity and overall capacity that you have installed. And within renewables, solar and wind are going to be the two largest components in terms of the overall energy production. Now, when you start implementing and installing more renewables, there's two main issues that you have to deal with. One is all of this uncertainty that having the renewals is going to be having, and the current design of the markets has some idiosyncrasies that actually exacerbate some of these components. The other one is that precisely because of that uncertainty, it might be that the contract that you expected to have at some point is actually not going to be available. And this is going to be leading to large forecast errors and, for example, large issues in terms of the dispatch of the electricity that you're going to be having. So this problem of variability and uncertainty in power systems is something that we need to grapple with. And I'm going to be focusing in this presentation mostly about the issue of renewables. There's other sources of uncertainty that can come from, for example, more demand participation, increased use of distributed energy resources, and, for example, interdependencies with other systems. So if we want to think about the directions for a low carbon economy, what we're going to be seeing is that electricity is very likely to be displacing other energy services. We're going to be having more use of renewable energy sources, more participation of distributed resources or distributed energy resources. It might be that we're going to be having more storage, and that would be something desirable in the sense that they can counteract some of the uncertainty and variability. However, there's also challenges associated with the scheduling storage devices. And it's possible that actually I'm an economist, so I'm always interested about new, for example, participants that can start helping us hedge some of the uncertainty that you have in the system. This is actually a relatively dated graph now by the Department of Energy of the US. And what we see is that there's going to be electrification in many sectors. That can include, for example, transportation, that can include, for example, provision of thermal services in the winter, like over here. Heating is still, in certain parts of the US, is still very dominated by natural gas and even oil. So it is possible that we're going to be moving towards heat pumps. And I mentioned about the resiliency, like for example, if you're going to be having larger events, how do you manage that system? How do you restore from those? And interdependencies is, for example, if we start electrifying transportation, how are you going to be managing with that demand? But focusing on the pricing, this is mostly for the electricity markets, considering uncertainty from renewables. One thing that we can look at in the history is that we have, as of now, the design of electricity markets has converged. So in many instances, what we have, like for example, over here, I am going to be mentioning the cases of the US, the Europe, and the Australia, New Zealand, is that you have a system operator that needs to, for example, receive the bids, or like for in certain cases, it may be even like a cost functions that they're going to be audited. And according to that, it schedules the resources and decides what the prices are going to be. And typically, this is done in 2 stages to manage the uncertainty. In the first stage, you may decide to start committing certain units. And in the second stage, you may decide the redispatch, which is actually when you are delivering the goods. There's variations, right? In the European market, there's no commitment. Like, like there is something a little bit different in terms of like how they're going to be scheduling the resources. But the most important thing over here is that the prices are going to be coming from this participation from the distributed or the different participants in the market, like for example, different generators, and the submission that they do to a centralized market that is actually going to be setting up the equilibrium between supply and demand. Okay, we have in certain cases participation of some demand resources. Here in the US, we call them load serving entities, and they may have some ways in which actually they express their willingness to pay or the willingness to accept certain interruptions, but that is still very limited. So again, the motivation of what this talk is going to be structured around is that we're going to be moving to a low carbon economy. So that includes the increased participation of renewable energy sources, which are going to be having more uncertainty and variability. We need, therefore, to create market designs that account for that uncertainty. And there's some challenges about that uncertainty and that management. First of all, is that not all of the participants are going to be having the same information, right? So like there's going to be some asymmetric information and we need to reach some kind of consensus in order to provide some services. There may be a distributed response from the different market participants. And we need to have provision of the services needed, not only the energy, but we need to maintain the ancillary services required to run the system. So the main questions that we're going to be trying to address is how to design markets that determine prices, considering the uncertainty and variability of renewable energy sources, knowing that we make this market non-confiscatory. So like there's not going to be, if you're going to be participating, you shouldn't be having losses, which is part of the social contract. And with that in mind, I'm going to be presenting a methodology that is forward-looking in terms of how do we come up with those financially adequate pricing schemes such that they're going to be uncertainty uniform in the real time. So the outline is going to be very standard. I'm going to be giving you a preview of the results. First, there's going to be some benefits. That is, like we're going to be using very limited information, so it's going to be easy for the consensus. And we don't need to start using scenarios. The real prices are going to be uncertainty uniform, and we have a guarantee of the financial adequacy of the system. And with this, we're also going to be increasing the locative efficiency and decrease the spare capacity needed. Now, there's going to be some trade-offs, right? First of all, it's having that financial adequacy may result in increased prices. And how to transition to this new system is something that is going to be challenging in terms of more organizational structures. So to give you a little bit of the background, like first of all, finding the right prices is a difficult problem. It is possible that you're not going to be having a unique set of prices, mostly because there's all of this uncertainty that I've been talking about. There's also non-convexities, particularly if you're still relying on technologies that whose unit commitment is going to be important. And there's different characteristics in the way that you can actually start using the prices that you obtain. So for example, you can use equilibrium prices. What I'm going to be talking in this chat is going to be about revenue adequate prices. Now, some of the literature of this is based on, like, for example, how have we restructured the markets, which I'm going to be entering into more detail in the next slide. Mostly in the academic literature, there's been a lot of interest about how to start integrating stochasticity. So we have primal dual pricing, revenue adequate prices, and semi-Lagrangian relaxations that have been suggested. And for example, if we're going to be having non-convexities, it might be that actually we come up with some way to price those non-convexities and come up with some minimization of the uplift payments. So there's been some works in we're raising equilibrium, and then some ways in which actually you're minimizing explicitly the uplift that you need to pay. Now, for the restructuring webs of electricity, which is probably something that you may have seen similarly in Korea, there's been maybe 3 main stages. The first one is that there was a myth of the natural monopoly, and the very first wave of the deregulation of the restructuring was trying like to debunk that myth, like saying that it was not possible to actually participate as in any other market. So like that was probably like the most difficult one, and there were crises associated to it. But then after all of the initial challenge of moving towards those restructured markets, we move into how to start improving that market, right? So like, how do we make it more efficient? The last wave, which is the one that we are in right now, is about incorporating that uncertainty, right? So like, like, and the uncertainty is from the sources that I had mentioned before, right? So like mostly I'm going to be focusing here in my methodology in uncertainty from renewables, but there's all sources of uncertainty, right? So like, how do we start trying like to make something that is stochastic more manageable for example, industry participants that want to have the certainty of a certain contract? Now, I'm going to be talking about like the assumptions and the formulation from my methodology. We are going to be thinking that there's a centralized market administrator, and there's going to be this perishable commodity goods, so like something that we need to use in a certain point. And we're going to be having producers that use conventional technologies. So like in this case, you can think your natural gas, your nuclear plants. So like they're going to be able to control whatever they're going to be producing. We're going to be using producers that use environmentally clean technologies, but they're not able to control what is the availability or what is the dispatchability of those resources, right? Like, I cannot control the availability of wind or of solar. There's going to be consumers that are willing to reduce. They have a certain demand, which is going to be inelastic, but they are going to be willing to reduce their demand if they're compensated for that. And there's going to be a product that isn't changed over an undirected network, right? So like this is going to be the electricity system. We need to respect the physics of the network. So like we need to make sure that Kirchhoff's laws are going to be respected in the market design from the very beginning. And then there's going to be some basic knowledge of the probability distribution of the random variables that are going to be affecting me. So I may know the mean and the variance of, for example, the load uncertainty or the wind variability. Okay. This is going to be affecting mostly the producers that are going to be using renewable energy. So let's start with a very simplified example. We have a producer with a certain good, which has a certain cost, and they have to satisfy a demand. The very simple problem is that you have a market administrator that is going to be trying to minimize the cost. And then there's going to be a producer that is trying to maximize their profit. And in equilibrium, the prices that I obtain from this equilibrium of supply with demand, which are going to be having a shadow price lambda, is going to be exactly equal to the price that each one of the individual participants is going to be having. Then I can get to a clearing condition in which both producers are going to be happy maximizing their profit, and the market administrator is going to be willing to dispatch at those levels, minimizing the cost. So we're going to be assuming that the market administrator is going to be maximizing the social welfare. The goods are going to be delivered over a certain network, and this is going to be an approximation because it's the DC approximation. We have uncertainty from the green producers, and the pricing should guarantee the revenue adequacy and expectation. The uncertainty modeling, there's different ways in which you can do it. Here, we're going to be doing based on chance constraints. Like some people actually have been using scenarios. So that's a more, like probably more papers have been into that area than with the chance constraints. Now, we're going to be assuming that there's a way in which actually we can transform that uncertainty based on the fact that we know that the error, for example, of the renewable energy is going to be normally distributed. And for that, we're going to be considering what is the ramping up and down that the generators need to do, and what is the dispatch of the renewable energy that I need, and how much of the supply or the total stated demand am I going to be supplying, right? So, in this case, this is going to be some load that may be checked. We're going to be minimizing the cost of the energy, the cost of the ramping for the different generators, the cost of spilling some wind, and then some compensation for the energy that is not procured. And this could be compensated at the value of lost load. So we have this expected operational cost, which is a very standard measure. The constraints on the nodes are the typical ones. So we need to make sure that actually the supply is equal to the demand. And like, for example, we're going to be satisfying this in day ahead and in the real time. The constraints on the edges are the flow over the network. The constraints on the supply are going to be related to, for example, ramping capabilities and like the limits of the generator. And the constraints of the demand is that if I have a certain stated demand, I want to be within certain limits. And basically, I don't want to shed all of the load that I have said that I want. We're going to be clearing this process. And then we assume that at least some of the load is going to be served. And that's the sum of all of the loads is going to be greater than zero, right? The sum of all of the loads served is going to be greater than zero. The pricing mechanisms allows me to find prices that actually satisfy consumers paying for the procurement of electricity in the day ahead, which is going to be with some factor that depends on the chance constraint, and in the real time, which is going to be this other price, which basically I put it like an inverse of the lambda, but that is going to be the real time price, and it's also going to be adjusted by the uncertainty. The conventional producers in day ahead are going to be paying the lambda of the market, and in real time they're going to be having the real time price plus a certain adjustment for whatever is the ramping up and down that they require. And the green producers, which are the main source of uncertainty in this model, are going to be paid a certain component that is based on the day ahead price, and then some components related to the uncertainty that they have. Right? And in real time, exactly the same components that we saw before are going to be playing, but then interacting with the real-time price, right? And like they say, in this case, they're going to be compensated for the shortages or surpluses that they provide. Overall, this is a comparison of the market mechanism, and I compare it to a case in which we have scenarios. So here are all of the prices that you get in the stochastic. In the chance constraint, the prices will be identical if there's no activation of certain extreme situations. For example, if ramping is not too extreme. In the real time, the main difference is that whenever you use the scenarios, you're going to need to take into account the probability of each one of the scenarios, which is this pi super omega that I'm showing over here. In the chance constraint, you don't need to worry about what is the scenario that happened. So I think that this consensus problem that I was talking about in the motivation is going to be much more easily solved. So some takeaways is that here I summarize a financially adequate pricing scheme that is not going to be depending on the scenario selected. The price signals are going to be allowing the managers to, for example, schedule their resources in a much more efficient manner. And for the renewable energy resources, they're going to be having, the managers are going to be having additional revenue streams that allow them to be more effective. There's going to be some extension to other pricing schemes, for example, that you can use based on chance constraints. Now, there's the policy issues regarding the protection of consumers from the price exposure, which is something that we saw here in the US with an extreme case like what happened in Texas with Winter Storm Uri. And some intertemporal effects, like, for example, what are the ramping effects between periods and adjustment costs. These are some of the references, and I look forward to the Q&A. Thank you.